Hi, vandaag gaan we een tandwielpomp uit elkaar halen.
Gentlemen, welcome back to the shop, and I dare say, the odd lady. Odd because if you're checking out a video about a hydraulic gear pump, chances are you can roll your own cigarettes and kickstart a Harley. My hat's off to you. As such, I trust you will not be offended by a couple of F-bombs and the odd dick joke. Und wat wir hier haben is a Pedro Roque made in Spain fixed displacement hydraulic gear pump. Excuse my mouthful. We're going to go over the inwards and outwards, and I'll show you every little bit of how this little baby works. It is ubiquitous in industry. Heavy industry uses tons of gear pumps, so it's important for us to understand things so that we know how they work. Now, this is a fixed positive displacement pump. That means that for every rotation of the shaft, there is a fixed amount of fluid that comes out. And as we can see, there's actually a mark here on the branding to tell you which direction is in and which direction is out. If and you didn't have that, there's two other ways to determine the orientation of in and out. The inlet is always going to be, oh that's odd. Never mind. What I was going to say before I was so rudely interrupted by the truth is the inlet is always larger than the outlet, except in this case where the inlet is smaller. Why would that be? Well, because this isn't intended as a pump at all. It's intended as a motor. No matter, we'll forge on because, as we all know, or you will soon find out, any hydraulic motor can also be used as a pump. Conversely, any hydraulic pump cannot be used as a motor. However, they can be used as a motor with one small additional part. Prepare to release the shmoo. We're removing the metric bolts, and we can see they're metric bolts on account of the head markings. There's a number there, 12.9. That's a grade, that's the highest grade of commercially available bolt. So this is a good and skookum 10mm coarse. I don't know what the thread pitch would be, but coarse metric bolt. And the back plate here is steel. We're going to take that off, releasing the shmoo and showing you what's going on. Sort of. And as you can see, the input shaft makes another shaft counter rotate. Now, why is that? Well, let's get into it a little bit further. And you can see it's been used, it's got hydraulic fluid in it. And there's the cavity and the sealing elements, bearings. Let me show you what's really going on. Okay, now we got our A part. I could tell that this is used on account of the kind of nasty oil in there. So I don't know if somebody put the backing plate on incorrectly or if it indeed is a motor, but there is a way to find out. We check this seal here. I'll explain that momentarily, but for now I want to have a look at the operation. Now, a pump like this is able to pressurize fluid up to 250 bar, 250 times atmosphere, which is 14.7, so right around 3,000 psi. And it's amazingly simple, actually. It consists of a body that has room for the gears and the bearings, and then it just has a front plate and a back plate. And we drive this shaft and it turns the gears. Now, if you look at this, when this gear is getting turned from the inlet, which is the big one, to the outlet, if we're turning it this way, what's happening is that oil goes in this side, so this is flooded from the tank. There's oil in here, but it's sealed along the periphery. So oil gets in between the gear here and then goes around the periphery. And for every rotation, it forces more and more in. You see that? Think of the oil going in here and it goes around the periphery and around the periphery. Now, the problem is, that's very simple, but the problem is, of course, you're going to have oil on this side as well that's getting jammed in the middle, and it has nowhere to go. So, if oil has nowhere to go and you force more of it, and more of it, and more of it in there, eventually the pressure rises so high that the pump explodes. So we need to do something about that. And this is what we do. We have a special bearing face. This is a DU bearing, so it's a Teflon, essentially a Teflon bushing. And that lasts an extremely long time because, of course, this is pressure oil lubricated. There's pressurized oil in there at all times. So what happens is the oil in between the gears comes up through the bearing race here, and then there's a gallery and it goes directly back into the inlet. So even on the high pressure that could build up here in the middle, it always goes to tank. It drains to the inlet, which is tank pressure. So if we install this, we can see there's a nitrile rubber, Buna N O-ring, a specially shaped one, and then a Teflon backup ring behind it in order to stiffen it up. And that keeps the low pressure side sealed from the high pressure side. And any bypass leakage from here, from the middle of the gears, goes up through the bearing surfaces and back to the inlet. That's extremely important, because if we didn't have this, the internal pressure would build until the thing leaked or blew up. As with most things in life, can't be 100% sure, but I believe this is a motor, rated as a motor. It would work as a pump as well, because the motor needs to turn in both directions. That means that the leakage path at some point can go to the high pressure side. The high pressure side could be either inlet or outlet. So the shaft seal needs to be able to take 3000 psi, 250 bar. Now this is just a single lip, little real soft, mild lip seal. However, what we have here is this bronze backup ring, which fits perfectly and turns this into a high pressure seal. There's very little clearance there. Well, there is no clearance when we put the shaft through. So it's nice and tight. And then it's retained by this Jesus clip. So this is a motor. And by taking a normal, just low pressure lip seal like this, and then jamming a backup ring in here, it turns it into a high pressure seal. And what that allows us to do, as I said, now that it's a high pressure seal, we can seal in 3000 psi. Without this, it'll only seal 15 psi. So that is the difference, my friends, between a hydraulic gear motor and a hydraulic gear pump. Now if you look at this pump, amazingly, there's no seal on the outside. It's just metal on metal. So how does this actually seal in pressure? Well, the way it does that is because the oil itself seals. Oil isn't just for lubricating. It's for heat transfer. It's for oxidation resistance. It's for all this other stuff. There's all these other functions of oil. One of those functions is sealing. Oil seals. So all the manufacturer needs to do is make sure that the clearance is close enough so that it can turn freely, not too tight so it can turn freely, but at the same time tight enough so that the oil seals. Now, how do you know if one of these is junk? Well, one, normally this seal will blow out and you'll have oil pissing out of there. But two, if it's not making any flow, it doesn't give you any pressure, generally, because you don't have a flow gauge on equipment, you have a pressure gauge. Now, there's something to be said about that, and I'll get to that. But if there's no pressure and the pump is suspect, it's 4 little bolts. You take it apart. If you see this housing, this is an aluminum housing, steel gear. Now, you see this housing is all scored up, you know it's hooped. You got to replace it. Gear pumps, they're a dime a dozen. This probably $90 retail. Like, it cost nothing. Now, I want to give you a little troubleshooting pearl here. Drop you a little nugget, as it were. Pumps do not create pressure. Pumps, any kind of pump, creates flow. So when you have a hydraulic device and it's moving slowly, the first thing, it doesn't matter, for whatever reason, the first thing people do is crank up the relief valve in order to get more pressure out of it. Pressure has nothing to do with speed, because flow is speed. How quickly a cylinder moves depends on the volume of oil going to it, not on the force on it. The force, the pressure, is only the resistance to that flow. I say again, pumps do not create pressure. They create flow. And pressure is the resistance to flow. If you take the line off here, off the backside, just take it right off, and then run this pump, what do you think the pressure is going to be inside the pump? It's going to be 0, because there's no resistance to flow. You're going to have schmoo blast into your face just like last Saturday night, but you're not going to have any pressure. By the same token, if you make a hydraulic system and you block off the outlet, if for whatever reason, say you put this directly into a cylinder and the cylinder moves. Once the cylinder bottoms out, it can't move anymore. What happens to that oil? The pump is still turning. It's still forcing more and more oil in there. What happens? Fucking explodes. You need a relief valve in any hydraulic system so that when you get up to a certain pressure, the relief valve shuttles over and diverts oil back to tank. So anytime you build a hydraulic system, you have to have a relief valve. Now, getting back to the port size that I mentioned at the first of the video, why would you have two different size ports? Because on the inlet, the pressure is actually lower than atmospheric. And when you suck on a fluid, you lower its vapor pressure and it could boil. That's called cavitation. Now, it actually boils at low temperature. And what cavitation is, it creates tiny little bubbles, and then those bubbles implode. When those bubbles implode, it takes a chunk of metal with it. So you do that millions, hundreds, billions of times, eventually you wear the pump out. So in order to mitigate that, what they do is they make the inlet bigger than the outlet so that when it's sucking from the tank, that is atmospheric pressure is pushing fluid into the inlet, there's less chance of it cavitating. That's a design feature. The inlet is bigger than the outlet to mitigate the risk of cavitation. Now, if the design of the equipment is poor, you will get cavitation, or if you're turning the pump too fast, you'll get cavitation, or if the oil is too thick because it's cold or it's incorrectly spec'd, you'll get cavitation. And cavitation kills pumps. What if you get an off-brand Chinese one and it doesn't have the ports are the same size because they want to be able to make them cheap and they just slap them on any which way, and there's no indication of which direction it should turn. That is, there's no arrow saying inlet and outlet. How do you know which way this shaft needs to turn? It's either got to be on a clockwise or a counterclockwise rotating motor. Well, how you do that is you take the basal platen off here, boop, like this. Well, you don't really need to because you can see the shaft coming through. You just got to consider the oil goes in and it goes around the periphery. So this one is turning clockwise from the shaft end. Conversely, if it were over here, if you looked at this and it were over here, it would need to turn counterclockwise. Now, knowing that, if you buy the wrong pump, say you have a clockwise turning motor and you need it counterclockwise rotating, all you need to do is split the pump, turn it around, making sure that your leakage paths are going to the inlet. Now we got the assembly in there correct. It's a small matter of torquing the bolts down. Click! Shongi's your auntie. Thanks for watching. Keep your dick in a vice. Release the schmoo! Sick.